I'll so let me explain the plan, and then we'll take it from there. So I want to talk a little bit, very briefly, about black hole thermodynamics. Of course, I'm talking about asymptotically ADS black holes, right? This is the topics. And of course, what we want to really know is how this connects to field theory. So I will spend some time talking about that. Then I want to talk about something. So let me. Okay, something called the Brighton-Lohner-Friedman bound in ADS. It's a result that was known in gravity for a long time, but now I want to connect that to instabilities. And one of the most interesting instabilities in Fermi liquid theory is superconductors. So this is my plan. So this is what I want to talk about. In the first lecture I said I wanted to talk about finite temperature. So this is one particular aspect of finite temperature ADS-CFT. There are many others, of course, that you should definitely take a look, like hydrodynamics, gauge fluid duality. So there are many aspects. This is sort of the one that I want to discuss. If there is time, then I will talk about some recent work that I've been doing that has to do with disorders. So that means, you see, this is already something that only condensed matter people care about. But I think ADS-CFT can answer that question very nicely. So if we have time at the end, I'll give you a 10-minute presentation about that, how to implement that in ADS-CFT. But this is my plan. Okay, so I have written, asymptotically ADS black holes. Well, not explicitly here, but let's start with the method. So it's just like a Schwarzschild black hole in flat space, only that the asymptotic region is ADS. So I will write it in different coordinates, and you have to excuse me. It depends. I'm following different. Let me also mention about literature. So I gave you some long list at the beginning. That was, again, meant to be very general, but I'll tell you, for this particular lecture, I have followed this review by Ramayo, Alfonso. So 1310, 4319. So some of the things that I've been saying are contained here. I also looked at, there are many reviews. Again, there's an abundance of reviews in ADS-CFT, and now for every different topic, there are many reviews. But the one that I like here, that I think is very concise, is by Horowitz. And I don't remember the number. I think it's 09. Something like this. But it's one of the early reviews on these topics, and it covers superconductors. And then again, if I have extra time, I'll talk about some recent, slightly more convoluted ones. Okay, the black hole in ADS, it looks exactly like the black hole, as I said, almost like the black hole in so I'm going to work in Euclidean slicing. So if f is 1, we have ADS. I'm going to be working in ADS 4 for the most part. At the beginning, I'm going to keep it general, but then I will take this to be two-dimensional. Because in condensed matter, 2 plus 1 dimensional systems are very interesting, so that's the motivation. But again, so f equal 1 is ADS. And then what we're going to have is essentially something like what you have in a spreadsheet, blackening factor sometimes. So Z0 is the horizon, and ZD is the coordinate. Remember, the coordinate goes now from zero, at the boundary is at 0, right? C equals 0 is the boundary, F equals 1 is ADS. And then as you go inside, Z grows up to it becomes Z0, and then this is the G00 goes to 0 that you remember from Schwarzschild in the general relativity class. Okay? So that's the black hole. The only thing is that, of course, as I said, when you go to the boundary Z equals 0, it looks exactly like ADS. That's the difference. Now we know that black holes, or Hawking told us, okay, Bekenstein already conjectured that black holes have some temperature, but Hawking was able to compute it explicitly. Can somebody tell me how do I compute the temperature of something like this, a gravity solution like this?
Surface gravity. Gravity at the surface of the horizon.
Okay, so you can compute the surface gravity. Okay. What else?
With the GTD term, right?
Yes. Okay, what do you do with GTD?
Either right.
You differentiate it? Yes. Okay, good. So I hope that you have seen this. Essentially, okay, I see some people nodding, so I will assume, again, this is something that I can show you in 2 minutes, so, but not in this stage probably, so if you ask me over coffee, I'll do the derivation. It takes, again, one differentiation, and if you want, you can integrate back, but that's it, okay? So what you want to do, the main thing is that you want this, now this is a Euclidean manifold, right? And you want it to be regular, that's all. You want regularity. The point that can be dangerous is Z equals 0, which is the horizon. Now, what you do, of course, in this case, you will find, so at Z equals 0, at Z equals 0, this becomes 0. So if I want to focus close to the horizon, I do Fourier expansion of this function, let's say. This is going to be 0, right? And then the first term is going to be F prime, and this is what people mention differentiation. So it's going to be like this, maybe the appropriate sign, okay, and more term. So I then substitute this geometry by this thing. And then it looks, again, it looks like this is closing, and what I need to do is to make sure that I redefine what I mean by radius Z, such that I have something that is going to be diffeomorphic to R2. Basically, so I want at the end, I'm going to go, so I'm going to schematically tell you what you do, and then again, if you want details, I'll be more than happy to provide that. I wrote some of them here, but, so then, okay, so I'm going to go from some Z coordinates to rho coordinates, and then what is going to happen is this part of the metric will become the rho square. This part, believe it or not, will be some constant that depends on F0. And rho squared, and then dt squared. So this t is Euclidean, so it's like a circle. So this has to be the rho squared plus rho squared d phi squared. And this has to have periodicity 2 pi for my circle not to have any conical deficit. Okay, that's it. From there, I get a condition on the periodicity of the subject that comes from T0, and that will be the temperature. So I'm going to write it for this background. It gives me d divided by 4 pi. Okay, that's the temperature of this black hole. Good. So, again, I can compute not only the temperature, I can compute the entropy. The entropy is area of the horizon divided by 4 times Newton's constant, which is t plus 1. So the area of the horizon, I take t, some fixed slice, and this is going to be a z equals z0, so I just evaluate. This is going to be, So again, it's the area essentially of this piece evaluated at z equals z0. So this term will show up. Essentially what we have is, so the area is L divided by z0 to the d minus 1, and then I'm going to call the integral here v d minus 1, okay, that volume. Then I still have to divide by 4g. But you see, the key thing is that I have z0. Z0 is related to the temperature, okay? And the other variable I have is L. L is related to N, the rank of the gauge group. So I want to rewrite my entropy that comes from a black hole as a field theory entropy. So again, this part we understood. The only thing that we need to is to look back in our notes and find how L depends on all these other different constants. Alpha prime, there's alpha prime here. Then this is connected to the temperature. So I say that I'm going to simplify a little bit. So the entropy already divided by this volume, so that will be the entropy density, is essentially going to be pi squared m squared t cubed divided by 2. So this is the entropy of the entropy density of this black hole. So of course you could have, I'm going to call this letter S. You could have, maybe not yet, but you can make sense of this. Okay, so let's try to. So this we obtained. This we obtained from gravity, but we believe in ADS-CFT, so this should correspond to a field theory. This should be the entropy of some field theory, and we know the field theory should be at temperature T, it should be the theory of the N equal 4 plasma, right? So let's see if this even makes sense. Okay. So the factor T cubed you could have guessed by dimensional analysis of the entropy being dimensionless, and then you have just divided by volume. Volume, the only dimensional thing that you have is T, so you have to come to power 3. Then n squared, if I have again a theory of matrices, I have n squared degrees of freedom. That's roughly correct. So this is not obviously wrong. So that's a good step. Okay. What I want to do now is to actually compute what the field theory. So okay. So let's put this in a box here. So this is the answer that I got from gravity, and I know that it's related to a quantum field theory of finite temperature. This should be the entropy of that field theory, but at a strong coupling. That's when gravity is a good description. Okay, so this should be the value at a strong coupling. Okay, and I want to compare that with something that I can compute, which is the value at weak coupling. So let's do that. So actually, zero coupling. So let's assume that I just have a bunch of fields, and I can compute the entropy that these fields produce, right? Okay, there's some. Okay, so so first of all, yeah, maybe I can give some introduction, some StatMech introduction about how to compute this. So which I will do. So let me write one formula, and then I'll write one formula. Minus for bosons. So this I hope that you have seen somewhere in StatMech class. But if not, again, this is something that is very easy to construct. Volume, and then I have the 3p 2 pi cube log 1 minus plus e to the minus. This is the frequency of the energy. This p, okay, this p is of course momentum. Okay, but the particles that we're interested in are massless, so this omega will be essentially p. Now this we can compute for bosons and for fermions. I don't know if, or you can look it up in some StabMech calculation, and there's some interesting thing with the Bernoulli numbers, etc. But the answer is completely known, and I'm going to. The answer is the following. So for a boson, log of z divided by the volume is pi squared over 90 in cube. And for a fermion, this, yes. No, sorry. This is capital Z, and this is the partition function of a gas of this boson fermion. Good. So V3 for fermions is a different number, but again, as I said, these numbers, these funny numbers, 790 and 720, sorry, and 90, they come from some transcendental integral, numerical integral here, but it doesn't matter. You can compute it. This is the answer. What we need to do is to put it together with the. We have to now count the content that we had in the n equal 4 multiplier, and that's it. So if I have now a non-abelian Good. Okay. So if I give you the partition function, you know how to compute the entropy, right? It's again some just t d of log of c. So it's just some StabMech calculation. So I'm going to write the answer, but I'm going to write it already in a way that is ready to compare with this the strongly coupled answer. Okay, so how many bosons we have in n equal 4? So we have 2 basically gauge fields. These are the 2. And then we have 6 scalars, right? So that allows me to write, and I have n squared of, because they are in UN. So altogether I have 8n squared. So the fermions is again the same. We know the same number just because we are this is supersymmetric, but essentially the counting here is we have 2 times 4 Weyl spinors. Okay, so this is my number of particles, and what I need to do is to multiply that by the temperature, this logarithm by the temperature, and find and differentiate. And what I will get is that the entropy after I sum is going to be 2 pi squared divided by 3 n squared t cubed. This would be the entropy of the free gas. Okay. So now what we can say, or what we can see, that X black hole equals 3/4 S n equals 4 free. So this is a calculation that we can, as I said. It really shows how the SCFP works. So we're discussing the same system, but we can go to a regime of parameter that was inaccessible, a strongly coupled regime, by doing the calculation on the gravity side. We use the black hole. And then we can even understand, obviously the numbers came out, or the scaling, sorry, not the numbers, but the physics came out correctly. The numbers are changing, but that's not the fact that the entropy decreases as you increase the coupling is not completely, I mean, it happens in some realistic system. It happens for n equal 4, but we can be very precise about this numerical transformation. So we can say that the entropy of the gas is a function of the coupling, and for coupling equals 0, this is the answer. And for coupling going to infinity, very large lambda, that is the answer. Okay? So now let me talk about the Drayton Freeman bound. Yes.
Until now, the examples that we have seen, so we have used the calculation on the gravity side to learn something about the field theory.
Yes.
But are there examples in doing the other way around? To learn something about gravity, computing something about field theory?
Yes, there are examples. I'll talk about one such example tomorrow. And let me just say it so that people can think about it if you want. So it's and the example is the Wilson loop. So you can compute it in the field theory exactly using matrix models. Localization plus matrix model gives you the exact answer. And reproducing that answer from gravity is very complicated, and it tells you that we don't understand how to do certain aspects of the string perturbation theory and perfect spaces. But it points out exactly where you're making a mistake, or where you need to develop new technology. Yes, that is. We also hope, of course, that understanding this will allow us to get to things like information paradox or complicated questions in gravity, but that is not been developed yet. Yes?
I have a question regarding the result. Can we make some, or can we have some insight about the fact that the entropy in the strong coupling regime is smaller than the entropy in the weak coupling regime? I thinking in terms of a statistical interpretation of entropy or something like that.
Right. So yeah, I mean, this is the entropy. This is precisely the goal, right? To understand that entropy is not the free. That interaction is reducing the entropy, and that happens in other systems. So but what we have also here is that we have a numerical prediction, if you wish. So IDSCFT predicts that if you take your supercomputer and put an equal 4 in the lattice and do it for large coupling, this is the number that you will get. And in fact, this is not completely wrong. People use some QCD analogy to see that there's also some changes. Okay? Yes?
In the calculation of the partition function, this is basically the run ensemble.
This is canonical ensemble, yes.
Canonical ensemble.
Yes, there is no chemical potential, it's just temperature.
Yes.
Temperature is fixed.
My question, why you don't do chemical potential?
Okay, I could do chemical potential. I will do it if I get to other question, but this is the simplest. This is the simplest part. So I'll show you the simplest calculation. Again, as I said, if we have time, which I'm now doubting, I will show you some really what I think is very state of the art how to handle result. There are things that are a lot fancier. Okay? Good. The Breiter-Lerner Friedman bound says that the mass of the black hole as L squared has to be greater than minus d squared. So what does this mean? If I give you a scalar field with m squared negative in flat space, depending on the level of sophistication, you give me different answers. So one, you can tell me this is not allowed, this is unstable, this is wrong. And there's a slightly more sophisticated that, okay, maybe you're trying to expand around a vacuum that is not stable, and there might be some stable vacuum. But in any case, it signals an instability. Now in ADS, the situation is similar, except that masses square are allowed to be negative, but not too negative. Okay, so they can be negative, but they cannot. If they violate this bound, then this would be a true instability. This sounds very profound and very complicated. It's very easy to show, so I will show it to you in one line. Okay, but the key thing that I want to point is that there is instability also in ADS, and when I'm talking about what I just said about you might be in the wrong vacuum and going to the right vacuum, etc., you have to immediately click with your ideas of Higgs mechanism and etc., etc. And we will see that this is all connected, and that's where I want to go. So after PF bound, we'll go to superconductors, but if you think of the superconductor as a sum and spontaneously broken phase, then you will see that this is all very nicely connected. Okay, so let's see how this works. A scalar field in ADS has the following action. So I'm going to be very sketchy with numerical factors. So dz, dx, and here d plus 1. So this one we wrote yesterday when we solved the equation. When we computed the two-point correlator, what we did was to solve this equation. And if you remember, we had solutions. One was connected to a source, and the other one was the response, right? So this is the same equation that we wrote before. Again, a scalar field in ADS. I already put the metric factors, and with mass m. So I'm going to make the following transformation. So I'm going to write z as e to the y. And I'm going to redefine my phi. I'm going to write it as e to the y d over 2 phi. So this is some rescaling of the field and rescaling of the coordinate. This is not fundamentally deep, but here's the answer, or here's the implications. Then this action becomes this. So it becomes dy. It becomes dy ddx dy phi curve plus m square l square plus a quarter d square phi square. Okay? Up to a boundary term that I threw away, but that's it. Okay? This is just a very straightforward manipulation. Now, what do we learn from this? Okay, this, if I look at the metric factors and everything here, is flat space. There is no z anywhere or y, extra powers of y. This is just a scalar field in flat space. And then I remember, but in flat space, m squared has to be positive. And that gives me this bound. Okay? So just by mapping a scalar field in ADS to a scalar field in flat space, I immediately realized that the mass in ADS has to be above this bound. Okay? But again, the goal is not to show you this transformation. The goal is to excite some neurons that will start putting a picture like that in your mind. Saying, okay, this is what negative mass means most of the time when life is beautiful, and then maybe we will find situations in which the mass square of the field in ADS looks negative, but it's essentially pointing to me that there will be some other vacuum that will be stable. And that's where the theory wants to go. So also people say the gauge field condenses, or sorry, the scalar field condenses. Okay, so that's the BF story. So now let's talk about superconductors. So any question about that? So what do you know about superconductors? So can somebody give me some one-sentence statement about superconductors? It has zero resistance. That's the good one. That's the most popular one. Sorry? They are cold, so it's a low temperature. No, but this is very important, right? So superconductors were discovered at the beginning of the 20th century, and most of the time it was because it was the technology to cool some metals became available, and many metals display superconductivity at low temperature. Okay, so but there's also a theory. There's a very beautiful theory behind superconductors that has to do with that Mexican hat potential. Over there, so I think it's nice to be in Mexico and studying Mexico. But so there's a theory like that. The theory was the effective theory was discussed by Landau and Ginsburg. I will write one action that will tell you yes, superconductors are doing some Mexican dance. And then there's also the story of BCS that essentially tells you that you have Cooper pairs that form. That's an instability of the Fermi liquid theory, and that essentially is again something some spontaneously broken symmetry. Okay, that's the more theoretic way to look at superconductivity. So let me start. So we want to discuss superconductivity. Obviously, in the context we want to connect to ADS-CFT. But let's very quickly discuss. So the Landau-Ginzburg theory essentially this is the free energy, and it says that the free energy, basically that the whole process is discussed is a second order phase transition. So let me second order phase transition, and that is governed by some order parameter. So these are key words that I want to translate. I'm saying them because I want to then go to gravity and say, what is the transition? What is the order parameter? All that I want to identify very clearly. So we have some of the parameter phi, some complex. Then Landau and Ginzburg told us that the free energy of the transition is really described by a functional like this. Alpha and beta are positive, constant. Now what happens, and this is essentially the big insight of Landau and Ginzburg, there are other stuff, okay, that has to do with RG. I will not go into that right now, but essentially the key thing is that you have two states, just like in that, similar to the situation there. For T greater than Tc, very high temperature, this potential this is positive, and then you have only one minimum, and the minimum is at phi equals 0. But as you lower your temperature for T less than T critical, then this becomes a theory exactly like that, and then there's a minimum that is non-zero. Okay, and that is what describes. Then you can try to connect that with superconductivity. Now, a key thing, because it's another important ingredient, is that we connect that with an associated U1 symmetry breaking. And that has to do ultimately with the photon becoming massive, etc. Okay, so now I want to tackle this question using ADS-CFT. Now, let's do that. But notice that, and this is something that I emphasize right away. So there are different approaches within ADS-CFT. So now I'm going to have a completely bottom-up approach. So there's some phenomena in field theory that I know takes place, and I want to mimic it, but I will not start with type 2B supergravity with all its gory details. I want to have a minimalistic description of that phenomenon. Okay, again, this is a position. You have to decide for yourself whether you like, whether you think this is a interesting line of research or no. I have to always stay within the more formal rigors of ADS-CFT as we discussed it the first day. But there are many, this is a burgeoning area, and the philosophy is slightly different. There's nothing that tells me that we are guaranteed to succeed. Okay, but you think, okay, ADS-CFT has succeeded in many places, so maybe it can do this. It can do this. Okay. So let's see. From this point of view, which I was discussing yesterday, it's a little bit like it's alchemy, right? So you're in the kitchen and you say, okay, what are the ingredients that I need? So let's look at the ingredients. So we go to now the gravity shop, and we said, okay, what are the things I need to create my superconductor? So the first thing that you need is temperature, right? So that one, of course, because we're talking about lowering the temperature, phase transition. So that means that I need to look for some black hole. So go to the black hole aisle, and the one that I showed you before is the right. Then what else do you need? So you need a condensate, at least to mimic Landau-Ginzburg. So you need something that would be the condensate. Okay? And this, of course, what we think is that there will be some scalar field that can do this for us. Because, okay, the other parameter, the operator, if you wish, is just a scalar. It's complex, but nothing. But now you see, once you mention this word condensate on the temperature and moreover on the gravity, then you have to reckon with a lot of literature that says that black holes have no condensate. Otherwise, the black holes have no hair, or the black holes have balls. So there's this idea, right? That there are theorems about this. So about the hair of black holes, because that's essentially what we're looking. What we call a condensate is something, some charge or something of this scalar. But there are many situations in gravity where this is known not to be the case. Yes.
Sorry, the critical exponent in the phase transition is exactly 1?
The critical exponent in the phase transition is exactly 1/2 in mean field theory, which is what Landau gives with.
And why does the 1/2 appears there?
This beta, no, these are coefficients. So this is because I'm going to, when I look for the minimum, I'm going to differentiate. The minimum is going to be beta or alpha or beta or something like that. No, it's not important. You see that the minimum is the square root of t minus tc, no?
No.
Okay, so let's look at the minimum of this functional. So I have 2 phi, and here I will have, okay, 3 phi cubed. So at the end, phi squared, and here I have t minus tc. So it gives me square root of t minus tc. Okay, we'll go back to this. This is an important question, so thanks. I'm sorry that I did not set it at the right time. So there's this question of hair, and now I don't want to go into many details. If you have never heard about this, don't worry, but the key thing is that in ADS, a lot of these theorems do not exactly work because ADS has a special boundary, the boundary of ADS. And this is really a very good exercise to do, to show that geodesics in ADS, they go to infinity, but then they bounce back to the center of ADS. So it's not like in flat space that things radiate all the way to infinity and that's it, they disappear. In ADS, that cannot happen. ADS is like a box. So light, anything can go far away, but then it bounces back and it comes. So it has this focusing property, and that's the one thing that allows us to grow some hair. Okay, so we are fine. Good, so we have that. And then I think we're done. So now what we want to do, of course, we also want some U1. So we want to have some U1. Just so that. So with this ingredient now we say, okay, can gravity give me an analog of that process? And let's see what happens. So I have to start with, now I want to turn this into some formula. So I'm going to start with gravity, again, in 4 dimensions, because I want to connect to 2+1 physics. And here's what I need. I need gravity with ADS. Okay, so I always put my negative cosmological constant so that my solutions are in ADS. And then I also say that I wanted a photon. There's a subtlety about this photon, but I will not go into that right now. I'll be happy to go into some detail if you're interested. So this is then I need a charge scalar or complex scalar that has to be charged. So I'm going to write it like this. Q is the charge.
So the U1 symmetry breaking you mentioned before is purely Landau history.
So Landau doesn't have a U1. Landau has this parameter. There's no gauge field, there's no FEF nu, etc. So, but that is in the picture. That is sort of, this is something that contains that in some sense. In the BCS picture, then once this thing is developed, we will see it also. Once this thing develop F, if it is charged, it will create a term here, which you can think of giving a mass to the photon, and then that's why things really decay. Okay, and then I can have some mass. So that's my theory, where I want to find a phase transition similar to superconducting phase transition. Okay, so good. So now let's connect to Breitolone-Friedman. So I need to find some instability in this theory that tells me, yes, your black hole at very high temperature doesn't want any kind of hair, but as you lower the temperature, it is possible that there will be some condensate for the skeleton. So let me give you the argument. The argument is also very nice. Okay. So what I need to do is I need to write the equation of motion for this system. So it will be Einstein, Maxwell, and scalar field. From the equation of motion of the scalar field, I'm going to read this quantity, which is effective mass. So it would be the mass plus. You see, this kind of Clifford already mentioned. This we know more or less from quantum mechanics. So the gauge field enters there. So and the 0,0 component is really what matters. So I will have q squared GTT AT squared. Okay, so this is the effective mass of my field. And GTT is negative. So this can, in principle, GTT is negative. It goes to 0 at the horizon. So close to the horizon, it is non-zero. But then the field, if the field becomes larger, then I can drive an instability on this system. I'm just talking about the gravity description, and that is indeed that's what happens. Okay, so this system has an instability. It wants to create at low temperature hairy black holes, and that we want to identify with the superconductor. But I will be a little bit more precise right now. Okay, so instead of solving the full thing of Einstein-Maxwell scalar field, and what I'm going to do is I'm going to take some prop limit. Again, you can, and people have indeed gone back and solved the whole thing with backreacting gravity, everything. The picture doesn't change much, but it's just simpler to get it in this limit. So one way to think about the limit is to say, so let me rescale a mu tilde divided by q. Scalar field will be some tilde divided by q. So if I do that, you will see in this section I will have 1 over q squared. Here I also get 1 over q squared. So here 1 over q becomes squared. This 1 over q squared times q becomes 1 over q squared here and 1 over q squared here. So I will have something that will be of this type: gravity plus 1 over q squared, Maxwell scalar. So that means that for very large K, for very large charge, right? For very large charge, this is a decoupled system, and I can just look at my Maxwell scalar system in that regime. Okay, and now gravity is fixed because it was not affected by this equation, and the gravity that we are going to take is, of course, the black hole in ADS, because we want temperature as one of our ingredients. So the metric is roughly what I wrote before. So I will not write it again. It's the same metric with temperature, nothing changes. And now what I need to do is to study this system in that background metric. So the equation of motions are essentially, okay, so I'm going to make an answer to simplify things a little bit. I'm going to assume that this field depends only, on R, and then the gauge field is only along the t direction, and it's like this. Then my system of equation, okay, let me write it, but so this is Maxwell equation, sorry, the Langford equation, and then the Maxwell equation is, you can write it here. So you see that if this field has a bed, it will affect essentially what we think of the electromagnetic field. Okay, so now what I need to tell you is boundary conditions, especially in the context of ADS-CFT. This is crucial. Okay, and what we want. So I'm going to write it. So essentially, what is going to happen is this. So asymptotics. Remember that the mantra in ADS-CFT is that all field theory information is read from here, from the asymptotic value of the gravity fields. Okay, so what are my gravity fields? So I had this phi, psi and phi. This can have a term like this and another term this. Okay. Sorry. Let me not change too much on this. This is Z, this is Z squared. And this one has mu, which is really the chemical potential. That because you see, I can convince you because what is the object, the operator that couples to A0 is G is the current, and that's essentially give me the right to call the non-normalizable coupling of this field the chemical potential. And then the subleading is the charge density, so I'm going to call it rho. And then I see. So that's all the physics of the boundaries here. All the field theory information is here. What I want to do, there's a subtlety here, but I will not even mention it unless somebody really presses me. But this is the non-normalizable mode, even though in this case it looks normalizable. But this is the non-normalizable mode, and this is the VEF of the operator dual to my scalar field. So what I want to do in a situation of spontaneous symmetry breaking is I want the source to be 0. Otherwise it would be explicit breaking. Okay, so I want to now solve these equations subject to these boundary conditions. I have to give you what mu is, but then the equations tell me what the answer, what the source, sorry, what the VEF of the operator is, and the charge density. And so there's essentially one graph. So now this is numerical, okay? So this is end of analytic. So I really now have to solve this for many mu. Mu determines, in some sense, the value of mu determines whether I am above or below the critical temperature, okay? And for each value of mu that I solve the system, I will determine the expectation value. So clearly, there will be some critical T above which there is no expectation value. So here I want to okay. So I'm going to write just side 2, but of course you have to think of this as the expectation value of the corresponding operator dual to this field, which in the Landau-Gisborne theory would be this phi. The expectation value is that phi. Okay? And what we see is that for very large temperature, above some critical temperature, there's no hair. There's no expectation value for the field. But as you go below certain critical temperature, you develop something like this. And then you can compute again in this region, in the region of the transition, you can compute what is the value of the critical potential, and the expectation value, and you again get T critical minus T. To the 1/2. Okay? So gravity reproduces for you mean field theory exactly with all details in this interesting transition. Okay? So any questions? Yes.
What is rho in the phi?
Okay, so let me be a little bit more detail. So in principle, what I need to specify at the boundary value of this field. So Z is my asymptotic value, Z goes to 0. Non-normalizable, normalizable mode. But then I can try to interpret what these values mean. And I gave you this argument that this is the chemical potential. And then I have to convince you that this is connected to the charge density. That's what I wrote.
The same goes for psi, I guess.
No, psi is a different field. You see?
Yeah, I know, but the criteria is more or less the same. I mean, I have to have a reason to ask for that asymptotic behavior for psi. I mean,
right. It's very good question. So you are looking for something. So you have to have some intuition of what you're looking for, and then you can look for it. You can find it. So, but this is a boundary condition. You have the system, but as Clifford said, the system is not much without the precise boundary conditions that correspond to this spontaneous symmetry breaking problem. Yes.
In the Landau-List book, when you include the fluctuation, you are able to get the correction in the system response. Actually, this formula would be more or less like 1/3 in 3 dimensions. But I mean, now can you map this? I mean, can you have a better correction from this picture, from the gravity?
I can improve this picture. I can improve this picture. Unfortunately, it doesn't go very nicely well beyond the mean field value. But this is, I mean, for one thing, I just discussed the prop limit. But again, if you do the fully back-reactive thing, this is going to give you more or less result. But there are things that you can do to try to understand corrections to clinical response.
Is it possible to write Lagrangian in the bundle?
Good. Yes, it is. The answer is so whether you can have a holographic Landau-Ginzburg. No, I mean there are some situations. Okay, so it's subtle because for example, following similar kind of analysis, people wrote the Tisa-Landau theory of the two fluid in the superfluid, not when you have the regular fluid and the superconducting and the superfluid. So certain things can be obtained. So they found the equation from gravity, but this particular, I mean, other things are not that clear. Okay. Yes.
What will change if I introduce back reaction? I mean, if I let the fields, the electromagnetic fields and the scalar fields gravitate, actually.
Yes, yes. So as I said, not much will change.
No.
People have done that already for many years. This is really important here. Okay, so I didn't want to, but this is really important for very low temperatures because at really low temperatures, then it becomes important to have gravity under control. Good. So, okay. So I guess. Okay. I think I now go to slides and I tell you a more. Okay. So this is the basic story. Now you can try to embellish it and to go to more interesting question from the point of view of field theory, etc. So I want to tell you a little bit about that. But please take it sort of like an impressionistic picture. Okay, so this one I expect you to really follow. Okay, here's the action, so what I'm going to say now is mostly research I do. So it's work that I've been doing in the last 2-3 years, and it will take a while to really follow this, but I hope to give you some flavor of where this research has gone in this direction. Just say the SCFT for this one. Okay. So I want to talk a little bit about, as I said, this is some research that I've been doing with some, first of all, let me thank my collaborators. So Daniel Arian is postdoc in Max Planck. Nacho is in Argentina, and Antonello is a condensed matter person from ICDP. And the overall question is, now you have superconductor. I show you the theory, the holographic theory of superconductor, and I want to answer the question of what happens if I put impurities? So how is this object going to behave? Impurities are a very important question in condensed matter, and I'm just using ADS-CFT to tackle that. Okay? So I will not go into a lot of details. So here's the big picture that goes beyond the actual calculation that I'm doing. So it's not completely clear what ADS-CFT will do. Some people thought that it will help solve QCD. It hasn't really. So for me, it's really very important to find the kind of questions to which one can apply ADS-CFT more loosely. Okay. One type of question is phase transition, because phase transition are fairly independent of the intrinsic properties of the system. So it's a point at which basically a lot of the internal dynamics is not very important, and there I think that perhaps ADS-CFT can be very useful in that situation, which is very good. Okay, and then because this has to do with fixed point of renormalization group, and I know because of Wilson that this is very universal, you can approach the fixed point with any theory. So in particular, you can approach with the gravity theory that claims to be a field theory. So why not? So for me, this is a place where ADS-CFT is as good as any other method to tackle. And then one key thing is that in this context, you see, we can discuss this critical exponent. We can discuss many things, especially dynamical things that are complicated to discuss in the context of just regular field theory. Okay, so then I have other motivation, but they are smaller. So let me stop here 1 second. So this is the model of Anderson. It's one of the really beautiful results or paradigms in quantum in condensed matter. So what Anderson did, considered this single electron moving in a lattice, and what he did, he put V, which is so V is some random potential, and what he showed is that this changes completely the properties of the system. So I want to basically, you saw today that there was Landau-Ginzburg, and for Landau-Ginzburg I took what are the ingredients and I constructed the gravitational dual of that. So this is what I want to do, what I have been doing in this series of papers. I want to construct the gravitational dual of this of this Anderson model. So something that will contain random energies of the on-site, for the on-site number of some particles. Okay, then people have tried, so this is a very interesting outgoing question in condensed matter, and this Vasco Leitner and Al Schuller discussed that in a long paper in 2006 that has set out in motion a whole subfield of condensed matter, this many-body localization. And what these guys are doing, different from Anderson, is that they're considering electron-electron interactions. Now, if I have a theory, as somebody gave to me a theory that says your theory contains a strong interaction, then definitely I want to see how it wants to play with localization and other interesting phenomena. Okay, so these are good. So here's where I want to start. So this is what I wrote before to you. I don't even write gravity anymore because I'm going to consider only the probe approximation. So I have Maxwell charge scalar, just as before. Okay, this I'm going to study the background of the Schwarzschild black hole. Z0 here was set to 1, just for simplicity. But this is another thing that I just wrote for you. And now what I want to do, because I want to study disorder, right? I want to study not a well. Okay, so because I want to start a disorder, now my fields, this is the answer that I would take. So before they depend only on Z, so now they depend on Z, and I want them to be, or the appropriate data should be random functions of X. So they will be something completely random, and that's my way of mimicking disorder in ABSCIT. But you see that conceptually, it's just what I explained to you. So this is my system, and now all my input is going to come in the boundary condition. These are exactly the boundary conditions that I wrote before, except that first these were some constant. Now these are going to be functions of X, okay? Non-normalizable mode, chemical potential, charge density, and then height. Now, mu and rho are space-dependent chemical potential, so that is for me to mimic this randomness. Okay, the functions psi 1 and psi 2 are identified on the duality with the source, which I want to vanish as a boundary condition because I want a spontaneous breaking of symmetry. And the VF of the operator, which is what we are out to measure. Okay. Now, then I have to put some regularity conditions at the horizon. The horizon is at z equal 1, as I mentioned. So I have to be very careful with this expansion, but nothing that you cannot handle. So again, my goal is to introduce disorder in this holographic S-wave superconductor. And what I need to do again is to promote the chemical potential in the holographic superconductor to a random space-dependent function. So why do I want to do that? Why do I want to make my life more complicated by looking to a system of PDE instead of what we had before, which was on ordinary differential equation? Well, the reason is that in particular the chemical potential, what it does, it defines the local energy of a charge carrier that is placed at position X, right? And this is like the particle number in Anderson model that I showed to you. So, which is of course the charge density and the number density in this system is similar. So this choice of potential really mimics Anderson charge number or occupation for a given site and the on-site potential. So this is precisely the holographic setup that will mimic a random, changing randomly the energy at different sites in a system. Okay, that's what I want to solve. And again, so I want to start something very close to Anderson, but in a strongly coupled system that like those described by gravity, it really doesn't matter much. So whichever way you introduce disorder, it will propagate to other operators that would be that's the situation. But okay, so this is really the key conceptual departure for what I just explained to you about just the holographic superconductor. So now how do I make this chemical potential a random function? So I'm going to choose this description. So mu0 is a constant, is what I did before. But I'm now going to add a set of functions like this, cosine of kx, k to some power, and delta random phase. So this, believe me, in the limit of infinite terms, this becomes a Gaussian. It's like a Gaussian distribution. So there are some physical parameters that I don't want to do too much on it, but the thing that I should measure, or the dimensionless quantities that are relevant, is if I want to discuss the strength of disorder, how much I have disordered the system, then I need to look at this dimensionless ratio, the amplitude of this part, the random part, with the homogeneous chemical potential. And then in the language of condensed matter, or solid state physics, this is essentially, this disorder is connected to the mean-free path. So it's increasing disorder is reducing the mean-free path, in a sense. It's very intuitive. Okay, now at this point, you have to put on some numerical hat, because this is not something you would do in a laptop like this. So, in fact, I did this with my collaborators, and in the University of Michigan has a cluster of computers, so I program this thing and I run there, and then I can do very good statistics, because this is a random discussion, so you really need to make sure that you develop decent statistics. And here's again some technical details of how good my collaborators are. Good, again, technical details. So this is already some of the results. So what happens, this is W, fortunately it's not cannot see very well, but this is the disorder, the strength of disorder, and the value of the condensate. So when the condensate at zero disorder is already large, then it grows a little bit. Okay, this is wiggly because I kept this for sentimental reasons. So these were my first plot from 2011 or something. My technology has become a lot better, so I'll show you what we can do now. But anyway, so this you can fix with statistics. But anyway, the trend is that the condensate grows with disorder. And there are cases in which it is zero with no disorder, and disorder essentially revives this. Okay? So this is actually something that at the beginning I was very puzzled, because you see, if I have a superconductor like this, right, something with non-zero VEF, and I start introducing disorder, I thought that it destroy the condensate, it destroys the superconductor. But essentially, in fact, then I start looking in the literature, and in fact, this is seen in experiments. So at the beginning, a small disorder tends to enhance a little bit, and there's some mechanism that I can go into some detail, but it's counterintuitive, but this is what happens, and people have checked. So we reproduce that. Here's the phase. So the superconducting phase sort of increases. Right now, as I increase disorder, this new part opens. Okay, so this is a little technical part, but let me tell you, because it also is really a very direct implication of ADS-CFT. So this is my chemical potential. Okay, it's this random function. I want it like that because I want to study the surface. But this is the response. And this is the response for the expectation value of this operator. You see, it's very smooth. So that tells you, okay, so then you can, but you see, now we can study these things very explicitly, because we have we just have to solve equation. I can now see, and I will show you in a minute, how this disorder renormalization is happening. That you have something very disordered, and so let's say that the output is very smooth. And the opposite can also happen for some other observables, like for charge density. The charge density is even more disordered. But I can give you numbers for this. I can give you tables like this. For example, here what I did, remember when I wrote the function for the chemical potential, I have 1 over k to the alpha, because I wanted to play with the power spectrum. So, and this k to the minus 2 alpha is the power spectrum of my signal, my disordered signal. And then I can read the power spectrum of the disordered signal for the condensate and for the charge density. And I see that there's this linear kind of relationship that I can make completely quantitative. Okay? So now, this is something that in principle you should be able to do in field theory. But in practice, it's very hard. But with ADS-CFT, I can just do it. I know the source, and I know the response, and I can compute it, and I can see the correlation. Okay, so these are the kind of things that one can do. I can do the same thing for the P-wave superconductor. It's a different title for the parameter. But so here's how much better my phase diagram gets, because again, with a few years, you learn to do these things much better. So now I'm going to talk about conductivities, and this is definitely the last topic. Okay, so we can compute conductivities in ADS-CFT, and what we need to do is to apply basically Ohm's law. So if I have a gauge field, the background gauge field, I can put some perturbation on top of it. Okay, time-dependent perturbation like this. Okay, and now near the boundary, this is the behavior. Now for this field, okay, you will see down here, but for this field, essentially this would be the electric field, and the response of electric field is a current, right? So if I divide these two, I will get the conductivity. So current divided by the electric field is precisely the definition of conductivity. But for this signal, I already know that this part is related to basically the source, the electric field, and the response is the current. So this will give me the conductivity. And of course, I have to put in going boundary conditions close to the horizon, and that has to do with causality. But okay, more condensed matter that you probably don't want to know about. But here is my disordered conductivities. Okay, there are some peaks. I can also explain these peaks. I will not go into detail because it's a little technical, but I can, and okay, so the black line here corresponds to homogeneous, no disorder at all. Oh, and then I have increasing disorder, but purple and yellow is the most disordered part. Then, okay, so I will not display this because it's a little messy, but we have a very good explanation and also numerical. Okay, it's not. So the explanation is here. It has to do with the second sound velocity in superconductors. But I don't want to go into that. But what I want to, as I said, this part of the talk is completely impressionistic. I want to show to you some of the stuff that ADS-CFT can do very explicitly in this context. Okay, so I can so the dots here correspond to peaks in the conductivity, so I can track what are the modes that are giving me this kind of peak, and then I know that they correspond to hydrodynamic modes of the corresponding of what I'm describing. Okay, so it's a very, very, very tight description. So now here's the slide about Landau-Ginzburg theory again, because now I can go back and I can answer a question that in field theory is incredibly difficult, which is what is the nature of the disordered transition? So that question, I will tell you what field theories do. Okay, I hope that nobody declares me persona non grata, but what they do is laughable, I would say so, right? And then I will tell you what we can do. We have the equations. I know how to put disorder in the system, and I can just compute. So let's see that. So this is, again, I just reminded you the Landau-Ginzburg theory. So here's what field theory people do. They use something called the replica trick. And this is how it works. So you need the replica, so you need something, and I tell you the reason why. You would probably, in any talk on disordered system, begins like this. So you want to find the average, not in the sense of partition function, but in the sense of energy. And because of that, it's not Z what you need. What you need is log of Z. You need to average with log of Z, because that's really what makes physical sense. But to get to log of Z, this is what you will use. You would say that log of Z is in this limit n goes to 0 of Z to the n minus 1 divided by n. So you have to now invent a field theory to do that will follow this recipe. So here's the action. This is 5 to the 4th theory, okay? OM, the OM model. I also discussed a little bit on it, but not much. So I want to put disorder in this term. This is like the mass, okay? And I need to tell you what is the distribution. Here is a Gaussian, but I can take whatever distribution. The thing is that when you integrate this term with this distribution, it will give you this new interaction. You need to have n copies. So this n is the number of copies of your field theory. You do that calculation, and then you send n to 0. That's the textbook recipe for how to compute disordered quantities in field theory. Okay? But now, if I give this to some of you, you think, okay, this is some many copies of the field theory with some fun interaction. Of course I can do this. I can what is it that I'm looking for? I'm looking for transition. I'm looking for a fixed point. Okay? So what are the couplings that I have? R0, U, and now this funny coupling delta. Of course I can write the beta function for those couplings. That was already done in the 80s. And this is the answer. So these are numbers that are known, but it doesn't matter. The key thing is that if you look at this equation, there are no solutions. So naive field theory tells you there is no disorder fixed point for the OM model. The OM model, I try to convince you that should be connected to what the kind of transition that we're looking for. Okay, then very smart people like Baranowski and Cardy came up with something new. They said, what happened here is that we need to use some double epsilon expansion. So epsilon expansion in the space, but also some epsilon expansion in time. Of course, I mean, is anybody else other than Cardy says this? I said, you're lying. That's nonsense. But nevertheless, you do it and then you find something. But you see, it's a very convoluted and I would say not very, I would say a straightforward approach to finding this fixed point. But what we can do, okay, this is on experiments. It doesn't matter. But I can compute the expectation value of this the parameter or the parameter in my theory. And this is what I find. I find that, so black again is homogeneous. Black is homogeneous. And then these are increasing disorder. Yeah, what this is telling me, I can be now more precise and try to see what kind of transition I'm having. So I'm going to try to do some fit So this is the one thing that works best. And what I see is that these are for 3 different values of disorder. And what I see is that the transition is happening according to some BKT type of exponent. So it's not power law or mean field as we saw without disorder, but with disorder, this is the kind of transition. So this is a type of question that ADS-CFT can answer. So I can extend this for more complicated systems like this thin film, but the key thing is that, so let me finish here. So this one we can push, and we continue to work on this with, again, Nacho and Daniel, and also with Johanna from Max Planck. But the program here is very, very straightforward. So ADS-CFT give me the opportunity and the framework to tackle disorder problems, and I'm going to push this. And as you see, most of what is required is just solving some equations and understanding what is the response for a given, for some given source or access. So I'm done now. Thanks.
We have time for some questions.
Is there any gravitational solution that has that behavior in the asymptotic? Because you had random function,
Yes.
a scalar field that behaves as a random function in the asymptotic.
Yes.
So, is there any gravitational interpretation for that? Or, I don't know, in the gravitational part? Can you say something about that behavior?
Yeah, I mean, so here's my, as you see, this is one of the things that I'm doing right now, trying to construct the fullback reactive solution. So people like Harno have computed this kind of solution, these disorder horizons are called, but with less ingredients, so without Maxwell field, just a neutral scalar and gravity, and they have found solutions like that, and they already understand some of the properties of the phase transition as well.
And the fact that it's periodic, it's not a problem either.
So it's periodic. It's periodic in the boundary directions in X, if you wish. That would.
Yeah. Okay.
So in Z, it does something else in
right.
Z.
Yeah.
Okay.
Why do we always forget about X-time?
Good. So that's a good question. So there are in fact holographic superconductors in type 2B string theory with all bells and whistles. So that you can do. The question is, or the approach is that for some questions that have to do with some specific dynamic, you don't worry about that too much because. And okay, since we have time, something that I have said in words during our talk, during these talks, but I have not shown an equation. And I think without equation, nothing gets through. So let's use, so a lot of what we have done in the course is to use, basically, we ended up solving gravity in ADS a lot, right? But you're saying, okay, what happens if we ADS? So suppose that I really want to do my 10-dimensional system, and I will have some scalar field that really solve an equation like this. So this one, because the metric is ADS5 plus S5, I can roughly split like this. Okay, then 5, more or less, because there's no work factor. And this, what I'm saying is that for most of the situation, then I'm going to do the following. I'm going to say that phi is some phi that will depend on the ADS part. Let me say it has some number L, and then it has to maybe some spherical harmonic on S5. So that allows me to then at the end I look at the equation as the equation of ADS5. So this will give me, let me say L plus 4 because I'm on a phi sphere, and this acts on phi. So more or less all the techniques that I have shown to you will work exactly the same for things that are spherically symmetric. Now, if you want to do something on S5, this is not true, right? So it will not be this is not a spherically symmetric. So there you have to do more. But you have to find the question. The key thing, and I mean, I said it at the beginning a little bit as a joke, but it's really not necessarily or not only a joke. It's, you need to know what question you want to ask. So you might have a question in field theory that has to do with some very complicated dynamics of the scalar fields. And the scalar fields, they are more or less translated into S5. Then you have to go into S5 and sort out what you're doing. But mostly you have to know your question very well before you can. And when you set it, then that's this. And what I've been discussing is things that are spherically symmetric on S5. So it's kind of like I can forget it because I can think of this also some effective mass in 5 dimensions.
Is there any symmetry in the Anderson model?
Is there any?
Any symmetry? What are the symmetries of the Anderson model?
Well, the model that I refer here, now okay, so it depends on the dimension. I'm not an expert, I don't know if some other condensed matter people know better, but my understanding is that people like Licht, some people have semi-solved Anderson model in 1 dimension. So there's some analysis there that is mathematically rigorous, but I'm not very familiar with it.
Please,